Okay, so we'll spend a little more time talking about viscosity. Um, Here's just a chart I made, just a hand-drawn chart of some viscosities, just so you could kind of compare them, up against each other, get a sense for it. So this is all dynamic viscosities, and so this should be mu. And the dynamic viscosities are all given here in kilograms per meter second, except for the meter second. So if you look here, we've got water, and you can see that the viscosity is fairly strongly temperature dependent. We're going from 0 degrees, 20 degrees C, and down to 100 degrees C. And you can see that as the temperature increases, the water viscosity decreases. So the water becomes less viscous, easier to flow, more easy to push around as you raise the temperature. And it changes by, almost a factor of 10 over that 100 degrees. Obviously, I have 500 degrees C down here. I don't have that here because that's not water at P equals 1 atmosphere. This is all at 1 atmospheric pressure, and obviously, water is not water. It's at that temperature. It's steam. So air, conversely, a much lower viscosity, as you can see, 1.71 times 10 to the minus fifth. Again, strong temperature dependence, but notice that the viscosity actually increases as temperature increases. So it's the reverse of the liquid water, as 1.71, then it goes 1.81 at 20 degrees C, and it goes all the way up to 2.18 at 10 to the minus times 10 to the minus 5 at 100 degrees C, and of course it can go all the way up to 500 C, no problem. That's 3.58. So we see again a strong temperature dependence of viscosity on temperature, but in the case of air, that viscosity actually gets higher. It gets harder to push air around. It resists flow more as its temperature increases. Engine oil, a much higher viscosity than either water or air. See almost like 100 times greater, almost 1,000 times greater than water. Actually, more than 1,000 times greater than water. Engine oil at 0 degrees, and it also decreases as temperature increases. So as the engine oil gets hotter, it flows more. Anyone who's played around with engines certainly has observed that cold oil is much more viscous, doesn't flow as well as warm oil. So in general, it's liquids and gases. So liquids tend to have or always have viscosities that decrease as temperature increases. And the reason for that is that liquids, the molecules are actually touching each other. What makes them liquids is that they are in contact in temporary, molecular bonds with other liquid molecules. That keeps them from flying apart. They have a cohesion to them. And so as you increase the temperature, you actually cause those molecules, those bonds, to be more relaxed. They break more. The liquid molecules are moving around more quickly, so it's easier for them to flow. That they aren't as bound, they aren't as tightly bound together. So liquid viscosities decrease at higher T, higher temperatures. They decrease at higher T, whereas gas viscosities. So gas viscosities are different because gas molecules aren't in contact with each other most of the time. They actually are far apart, rarely interacting, and so those gas viscosities are going to increase because as you raise the temperature, the gas molecules actually go faster and they hit each other more. So gas viscosities viscosities actually increase at higher T because there's more molecular interaction. Intermolecular interaction at high temperature. So this is all with pressure being held constant, but those molecules are going to be moving faster, and therefore they're going to be hitting each other more. So they're going to resist flow more because they're simply touching each other more, interacting with each other more, and that's going to increase their viscosity. So that's a big difference between gases and liquids in terms of viscosity. Important difference. The other type of viscosity that we're going to use in this class is called kinematic viscosity. So kinematic viscosity is related to the original dynamic viscosity. Its symbol is nu, so that's a Greek letter N. Do not get it confused with V. V is y velocity. So it's not that. It is a nu, which has this little loop on the end of it. So that little nu is called nu. and it's a compound property. So it's made up of two things. It's made up of the dynamic viscosity mu, and that's divided by the density. So that's your nu. And kinematic viscosity behaves a little differently, right? So we're going to have, if you compare those two things, let's say we'll have put T over here again on the left, and we'll just look at 20 degrees and 100 degrees. We'll do degrees Celsius. And then we'll have water, and we'll look at mu and nu. So mu, of course, we know this is kilograms, meters, seconds. And then nu, the units for that are meters squared per second, the SI units. And we'll compare that to air. So we'll have air here, over here. And again, we'll have mu, kilograms, and meters, seconds. And nu in meters squared per second. So if you look at this, we already know that the water mu, 0.001, that we've seen multiple times now. But if we go to nu, of course, we're going to divide that by the density of water. The density of water is 1,000 kilograms per meter cubed. So that's going to decrease it by a factor of 1,000. So that's going to be 1 times 10 to the minus 6 for the kinematic viscosity. And then similarly for air, of course, you have, for the mu, you might remember we had 1.81 times 10 to the minus 5 kilograms per meter second for mu. But for nu, you divide it by the density of air, but the density of air is actually about 1 at standard STP. So you've got standard temperature and pressure. So you got 1.5 times 10 to the minus 5. That is nu and mu are very, very similar for air, because the density is almost 1 at that temperature when you're at standard atmospheric pressure. So, and then if you take it up to 100 degrees, then for water, you get this viscosity will decrease, as we know, because liquid viscosities decrease as you raise temp. And we see that the density, of course, really doesn't decrease at all or increase, because the density of liquid water pretty much remains constant. So there is a small change in the density, but so if you do it all out, it comes out to like this. So we see that the dynamic viscosity decreases by quite a lot, and also the kinematic viscosity decreases, essentially the same way, because the density really doesn't change very much. On the other side of the house, we have 2.18 for times 10 to the minus 5 for the mu of the air. And then when we go to the nu of the air, 2.3 times 10 to the minus 5. So once again, a very, very small change. And almost the same now, again, because the density still isn't that different, and it's around 1, so we see a small change in that viscosity. So we can see that for liquids, nu and mu change similarly, because rho is basically constant as temperature changes. There can be differences in gas nus, because the gas density also will change in addition to in addition to the change in viscosity. So we see that. All right, so most importantly, that mu of liquid is greater than mu of gas in general, and nu of water is actually less than nu of air. So these are important. So in general, we have that mu of liquids are greater than mu's of gases. So mu liquids in general are much, much greater than mu's of gases. That is, we see much higher dynamic viscosities for liquids than we do for gases. Liquids tend to resist flow much more strongly than gases do. But the dynamic ones, nu of water, is actually less than the nu of air, because that density of water is so much greater, because the rho of water is so much greater than the rho of air under standard STP conditions.